Shall we get started? So this is the last lecture, and here we're going to just describe a few keywords that you will hear about and you will see in the literature. So there is no, we're not going to discuss any technicality because this goes beyond the scope of this course, and also it would take quite some time to discuss the details of these things. But I think it's useful to have an idea of what is out there, and to be more familiar with some of the more recent techniques that people use. So the title is really DFT beyond the local density approximation, but it's also like calculations beyond DFT, really. Okay. So let's get started with the first bit that we mentioned already a few times, both in the lectures and also discussing with some of you. So let's say the next level up with respect to the local density approximation in the exchange and correlation energy is what is called the PBE exchange and correlation. Okay, so PBE is simply the acronym for the names of the authors of this paper, which are Paradim, Burke, and Antroff, and this was done in 1996, and is essentially a technique to go beyond this form of the exchange and correlation energy. Okay, so the way I'm writing this here is exchange and correlation energy in LDA is what we've been using so far is basically a function of the density only, density of electrons. So at each point you have a certain density, then you from that you generate the exchange and correlation contribution coming from that point, then you add up everything in the unit cell, let's say. So that's the recipe in the LDA. So I'm not giving you the form of that you find in the book, but it's basically a function of at each point you have a value. Now, in the what is called generalized gradient approximations, okay, of which PBE is one member of the family, what is the idea is to basically to not only write down the energy as a functional of the density, but also the gradients of the density. Okay, so if you have a situation where the density is very, very slowly varying, maybe knowing only the density at each point is fine. But if there are wild variations in the density, maybe it's better to also take into account the slope of this change. So in this functional, actually, this is written just symbolically as functional of the density and the gradients. In practice, the situation is not that easy. If you go to this paper, you will see that the actual form of the functionality is quite complicated. Okay, and that was obtained by using very, very serious theory. And it's importantly, what I would like to stress is that that's entirely from first principles. So there is a parameterization in terms of of this density and gradients, but one only uses exact sum rules, basically, to determine this the various coefficients. So this is ab initio. Okay. So the reason why this has been popular is if you look at the binding energies. Okay. It does much better than standard LDA. So here in this plot, this is taken directly from their paper. So they have a table like that. So I just put down the experimental atomization energies. So what does it mean is that if you have a molecule which has more than 2 atoms, the atomization energy is the difference in energy between the energy of the molecule and the sum of the energies of each of its atoms. Okay. So that's the measured values. Okay? And this, what you see here, instead of giving you the calculated values, I'm giving you directly the difference between the calculation and the experiment. So in the case of the LDA, the blue line is the deviation, okay, in electromoles from the experiment, and in PBE, the deviation is the red line. So for instance, if you look at CH4, in this case is the deviation in the case of LDA is maybe 1.5 or 2 electromoles, okay, deviation from experiment. So that matches with what we've seen for the binding energies of chlorine and nitrogen. So there was an overestimation of about 1 volt in that case. And if you do PB, you see that the deviation is very, very small, a few tenths of an electrovolt. So you will see also that there are regions where PB does not do very well. So there are some error which can be quite large, but in comparison, I mean, it's certainly way better than the LDA. So really, this was essentially the first step to move from towards things like quantum chemistry accuracy, where you try to have energetics correct, below to within 0.1 electromoles. So that has been a very important advance. So at the beginning of the course, I gave you basically a citation analysis of this work until 2010. So now I basically added the data from Google Scholar until 2015, so last year. So you see basically this has been used 9,000 times last year, and this is, it's up and counting, so it's not going down actually. So clearly this is something which is essentially used pretty much everywhere. It's a very standard tool. As the number of people increases, also the number of users will increase, the number of citations will increase. So it's a very powerful technique. And there are clearly some variants. There are also developments of a PBE for solids specifically. So there are many other possibilities. But that's just to give you a flavor of how many people use these things every year. And I would say that, this is basically one of the most widely used techniques. The advantage, apart from the total energies, is that if you look at the structures, equilibrium structures like bond lengths, it is pretty much similar to LDA. So we see in LDA that we were underestimating lattice constants and bond lengths by maybe 1%, 2%. So with PBE, things go the other way around. So maybe they overestimate by 1% or 2%, but we're still very close to experiment. So one improves the binding energies and the atomization energies, but does not sacrifice the structures, okay? So that's the reason why it is very popular. Then some of you asked me about, in several occasions, about something called DFT plus U. So I would like to say a couple of words about that. So this is a technique which was developed by these authors here. And then there are, so that was, it's what, 25 years old. And there are many modern implementations, essentially. So in the first implementation, the situation was, slightly complex for an implementation in a software. So there are more modern implementations which take into account, for instance, the fact that when you add these features, they should be invariant with respect to how you orient your sample, which was not the case in the original kind of developments. So there are many possibilities for implementing these today. And the main idea is that these things were developed to address systems where you have magnetism, but mostly systems where you have magnetism in elements of the transition metal row, so so 3D elements, or the 4F elements. So in both these cases, so I think if you think about it, what is unique about these two rows is that the 3D states have no nodes, okay? So if you look at the 3D states here are the first time you meet the D states in the periodic table, okay? So that means that the wave function is nodeless. So the electrons are very densely packed towards, near the nucleus. And here, this is the first time in the periodic table you meet the 4F elements. So therefore, also in that case, you have no nodes, and the electron density is packed. So these are highly localized electrons. And for this, it is useful to use this technique. Why? What we described at the very beginning is that the way, so DFT is really a kind of building on the Hart-3 approach, where two electrons don't interact with each other directly, but one electron contributes to the total density. From that, you get the electrostatic potential, which feeds back on all the other electrons. So if you have two electrons strongly localized on the same site, they don't see each other directly, as it should be. Actually, one sees the other as part of a global density. So in some sense, the Coulomb interaction is a bit diluted, okay, by doing this kind of mean field procedure, where basically you collect the total electron density, and then from that you generate electrostatic potential. So there is no pairwise interaction, Coulomb interaction between these two electrons on the same site. So as a result, when you do calculation, that tends to delocalize the electrons, and they don't come out right, okay? So it essentially underestimates the Coulomb interaction energy on site. So this is one of the aspects, and let's say it's maybe the most critical one. So what this technique does is to add essentially a Hubbard-like interaction in these cases for these electrons, which fixes this problem. Okay. Now the way it works is really not as a global functional which is there acting on all the electrons. It is really a term which acts on these electrons and these electrons locally. Okay. So it's really written as a projector. If a wave function has a component, let's say, of 3D, that part gets a boost, let's say, in terms of Coulomb energy, so it's lifted up or down, depending on the, whether it's occupied or unoccupied. So basically, it's a way to apply, let's say, a patch to DFT, which correctly incorporates Hubbard physics, like lower rubber bands, upper rubber bands, and these things. And this is done as a, let's say, again, as a patch. So there is not a general, DFT theorem which, puts everything together. So this is essentially an extra thing which comes from the side. It's clearly mostly important for the physics of strongly correlated materials. It has been used very, very widely. So in many cases, without that, you cannot achieve even a qualitatively reasonable description of the system. So that has become important. Let me make an example. So this is iron oxide, one of the simplest transition metal monoxides. So the ground state is AF2 type phase, so it's an antiferromagnetic phase. So the way it works basically is that along the 111 plane, which is along the diagonal of the cube, okay, so if you have the planes which are the 111, the iron atoms have all the spins ferromagnetically aligned within the planes. Then if you go to planes, so if you move along the 111 direction, so adjacent planes are antiferromagnetically aligned with respect to each other, okay? So basically just an antiferromagnet. If you do a standard DFT calculation, okay, without these corrections, you get a metal, okay? It's just a metallic system, okay? So that creates a problem because you don't have antiferromagnetism. It's really qualitatively incorrect. And if you use this technique, which is LDA plus U in this case, I'm putting in blue the gap. So basically, you open a gap in the system. So now it becomes an insulator, and it is correctly antiferromagnetic, okay, with the correct structure, actually. So this is basically, the kind of things you can do with this technique. And I think the main object here, the main point of interest is that if you do a calculation with a band gap which is slightly wrong, you can still make a discussion about your system. Maybe qualitatively some other things are okay. But if you want to study an antiferromagnet, which is an insulating antiferromagnet, and you get a metal in the calculation, you just have to stop there. There's no way to say anything meaningful. So this is basically the way to proceed in these cases. So the other thing, the reason why it became widespread is that it's very efficient computationally. So the overhead compared to a standard calculation without the Hubbard corrections is tiny. So you won't even notice if you try to. So if you add these kind of flags in the input files, you will not notice the difference. I mean, for some big systems, you will notice it, but in general, it's not a big overhead. One problem is the following, is that there are techniques now discussed in this work where you can determine, okay, the Hubbard U parameter, this kind of correction term, from first principles, okay, using a linear response technique. However, that is not used by many groups because it requires some complicated calculations, okay. So as a result, many groups are using the Hubbard U parameter as an adjustable parameter. So what you will notice is that the size of this gap may be, or if you're studying defects, things like that, they will be quite sensitive to the Hubbard parameter. And in order to kind of fit experiment or something, or go close to experiment, there is a big temptation to, trying to adjust the parameter so that you get a reasonable answer. So in practice, the problem is that the results typically are quite sensitive to this parameter. So the bottom line and the take-home message for this slide is that whenever one presents results calculated using DFT plus U, it is really important to ask for a sensitivity analysis where you show that the main conclusions do not depend on this parameter. because if they depend on this parameter, it means that you can get any conclusions you want. Okay, so that's I think something that is becoming more mainstream. So at the beginning maybe it was not that well understood, the sensitivity. Now it's becoming so people are becoming more careful, and people are trying to understand really the potential and the limitation of this technique.
Do we have GGA plus U?
Yeah. For every functional, basically, okay, you can add the U, let's say the Hubbard U correction. It's really, it's essentially independent of the underlying functional. It's a different, it comes from a different point. So it's, then I would like to move on to something else, which is hybrid functionals. I'm putting these slides because I'm sure that you heard about this name, so it's useful to maybe mention it. So these are probably the most common, and you can recognize some of the usual names, basically developing functionals. So one is the PBE0, one is the HSC functional. So let's just try to see what this is about, okay? So in practice, the idea is that all the functionals based on LDA and GGA, they only look, so the potential, let's say the electrons are filling, depends only on the density on a certain point or the gradient of the density. But if you remember about the many-body Schrödinger equation, there were Coulomb interaction between an electron here and an electron there, so very non-local interactions. So you were not depending on what was happening near you, but something very far away. So that can be incorporated actually by including the Fock exchange energy into the description. So this is something that we mentioned on the very first lecture, where we described trying to solve the many-body Schrödinger equation using a slated determinant, and that was leading to the Fock exchange contribution. Okay, in DFT that is replaced by a local function, okay, because that was expensive. And now there is this idea that well, maybe computers got faster, we want to be more accurate, so maybe it's time to bring back this Fock exchange. The main problem is that it's no longer a function. So here you see it's an integral of two variables. In the functionals I showed in the first slide, you had the integrals on only one variable. Okay, so this basically depends on two variables, and maybe I can show you this. Essentially, what happens is that in the actual Kohn-Sham equations, when you're looking at the exchange potential, so it's no longer something like exchange of the position of the electron, but it's something which depends on the position of the electron, the position of another electrons. Then you apply to the wave function, and then you integrate. So this was done like that in the standard local DFT. Essentially just potential multiplying a function. So that was the bit of Hamiltonian coming from the exchange. And with the Fock exchange, it becomes something where it's a non-local function, and you apply it by performing an integral. So that, you can imagine, it becomes quite expensive. So numerically, it's very, very heavy. Okay, so that's also why you don't see too many calculations yet done this way, but they're becoming more and more popular. So this is the complete Fock exchange, okay? And that's something which was, is using the Fock exchange and no correlation at all, was the way people have been doing molecules for decades, after the discovery of quantum mechanics. The problem is that the exchange energy, so the exchange contribution, tends to open gaps too much in your systems. Okay, so it's not too good. So the prescription in this technique here is the following. Let's keep the correlation energy from PBE, what we described before, and then let's do a mix of the exchange energy from PBE and the exchange energy from the Fock, and do 3/4 and 1/4. So there is there are reasons to do. There are reasons to do this, and this actually has been derived from first principle. So it's the
3/4 and the 1/4.
Yes, there is a way. It's basically something. There is a theorem called the adiabatic connection fluctuation dissipation theorem. You can work with that to obtain these numbers, basically. So basically, this is a recipe where essentially I'm mixing a bit of Fock exchange and a bit of local exchange, and that's what is called a hybrid function. It's hybrid because it takes local DFT and non-local Fock exchange, and it blends them together. Okay, so that's the idea. And maybe just to
Do you want to turn your microphone back on?
no, it's already on.
Oh.
I mean, I never switched off. And I mean, from an intuitive point of view, I mean, you can think that this kind of functionals, Fock exchange will try to increase your band gaps, and PBE gives you too small a band gap. So when you mix them, you get something which is clearly more in the middle and maybe good enough to describe experiments. This is one recipe. The other recipe is the HSC. It's basically the principle is similar, but there was the observation that to calculate this potential takes a long time because it's a completely non-local object. Okay, so it's really numerically difficult. So the idea of HSC was to basically break the Coulomb potential, let's say 1 over r, into 2 bits. One long-range part, okay, and one short-range part. So essentially, it just multiplies that by an error function and then a complementary error function. So just write as a sum of two things, long-range, short-range. The idea is to do the short-range part, you do a 3/4, 1/4 mix, so PBE and R3 Fock, and the long-range part, you keep the PBE exchange, okay? So the reason for doing that is that if you're using a code which is based on local orbitals, evaluating that is quite quick, okay? And this is not problematic, all right? So basically, in this case, you gain a lot in terms of speed, as opposed, compared to the previous functional. So this applies to local orbital codes, but in the case of plane wave codes, the situation essentially doesn't improve much, okay? So these are the two hybrid functionals that mostly in use, but there are many other variants. This is basically a kind of a comment on these functions. Band gaps tend to be closer to experiment because with Fock you overestimate, PBE underestimates, you go towards the middle. And there is a lot of studies now which are benchmarking band gaps, like you do calculations of a lot of systems, you compare it to experiment, and you decide if this functional is good for band gaps or not, something like that. One of the problems, the advantages, let's say, or the problem is that so this fraction 3/4, 1/4 is something you can modify if you want, okay? There is no formal justification, but clearly if your band gap is too large, suppose, maybe you can reduce the fraction of Fock exchange and you can hit experiment. So that's a way of fitting a posteriori. So that fraction can become a parameter that you can use to get closer to experiment. So this is becoming quite popular in practice. There are different schools of thought here. You want to be a purist and not go fitting things, or you might say, I use this as a fitting parameter for a property which is well understood because my experimental colleague gave me this property, and then I using this fitting parameter, I study other properties which we don't know very well. So that's a way to get closer to something realistic, let's say. Then it's up to people to decide what they prefer. And from a fundamental point of view, in these hybrids, what one is bringing in is the Fock exchange, okay? But there are two things which are missing still. One is van der Waals corrections, and the second one is dynamical effects. So we're going to describe that in the next couple of slides. So this is something you cannot just bring by a mix of two functions. It requires going to a higher level of theory, okay? So let's maybe discuss van der Waals and dynamical corrections. Before going there, I just want to mention these functionals actually, apart from the mix, which seems a bit odd, they're becoming very popular because they give quite good structures, binding energy. So essentially, the more information you put in your description, clearly, the more the higher a chance you have to do something more accurate. Okay, the price to pay is that they become more expensive. So this is the point. So van der Waals interaction is something that you heard of most likely. It's something which maybe in the world of condensed matter physics and material science, let's say condensed matter physics has become kind of well known because of layer materials. Essentially, the interlayer binding energy or the interlayer separation, they can depend a lot on a careful description of van der Waals interactions because that's the kind of bonding you have there. So you will see a lot of description of van der Waals interactions. Here I'm going to give you, a very, very trivialized kind of explanation, which actually is not too far from what really, van der Waals interaction is, but it's an extremely simplified model. So in practice, if you consider essentially two hydrogen atoms like this, apart from each other, imagine that they are a very, very large distance, okay? So it is reasonable to assume that, in the ground state, there will be a 1s wave function here and a 1s wave function here, okay? So they don't touch each other, they don't see each other. So you can write down a many-body wave function simply as a product, as we did at the very beginning, product two 1s functions, okay? So that's fine. And then you can write down the many-body Schrödinger equation, the usual thing, like kinetic energy of the electron, this electron, the proton, and then you have the Coulomb interaction proton-proton, proton-electrons, electron-electron, as usual. So this is a possibility, okay? And this is a very simple guess for the ground state. There is nothing really. In this case, if you try to represent the electron density, okay, at each point, you find something where this is basically this shade is the 1s, a slice of the 1s wave function, the same there. And I just put a circle just to signify that that's essentially a spherical symmetry around the nucleus, okay? There is nothing complicated. Now, this is pretty much what you get if you do a DFT-LDA calculation, okay? So that's how DFT-LDA would see this system. And that's it. Now, if you go to this exercise in the book, actually, you can go by hand through the exercise. You will see it's a very, very simple exercise. And actually, I took it from a book of Enrico Fermi in 1930, which is called The Molecules and Crystals, in a spectacular book where it does these derivations in 3 lines. And basically, what it shows, it shows something, actually it doesn't give all the details. It gives basically the answer, assuming that everybody would understand it immediately. But the point is that if you try, you have a wave function, you can try other wave functions and see whether they give a lower energy when you sandwich in the Hamiltonian, okay? And in practice, what you find out if you follow this exercise in the book is that if you take a different wave function, which is what we had before, so this one, okay, plus an admixture of p states, so states which actually are oriented along the proton-proton line, okay? If you use an admixture like that, where this is the polarizability of the atom, okay, what you find is that this actually is a better ground state. So the energy of that is lower than the energy of this kind of spherical distribution. So if that energy is lower, so clearly this is a better guess for the ground state. There is no choice there. Now, how you get to this shape, it takes some reasoning, but the point is that once you have a better ground state, well, you need to discard the previous one and use this one. If you use that, what happens is that when you go calculating the electron density, using the techniques we said at the beginning, like square the wave function, integrate, and so on, in this case, actually, the distribution of density is no longer spherical, but it acquires a little bit of kind of elongation along the direction between the two atoms, which actually makes sense because, if you have a problem which has some kind of symmetry along this axis, so you expect it not to be spherically symmetric with respect to each point, but actually have a symmetry like cylindrical symmetry. So if you plot that, you get something which is slightly elongated. Now, if you now look just at the electrostatic energy involved in this story, that corresponds to an extra interaction energy, which goes as with the reciprocal of the 6th power of the distance, okay? And that enters basically the internuclear force in this system. So that's basically the van der Waals interaction. So in a sense, the van der Waals interaction is simply the fact that a non-interacting ground state, so using non-interacting independent particle approximation, using DFT-LDA type techniques, doesn't give you a good enough ground state. If you include a better, essentially, other terms, you get a better guess for the ground state. And the most important bit is that this function is, let's say, not correlated in the sense that there are 2 independent wave functions, okay? It cannot, this complete expression cannot be represented as a product of 2 functions. So if something cannot be written as a product, it means that it's a correlated wave function, okay? So when one talks about correlations, one thinks about some monsters or something very difficult, but actually this is maybe the simplest example of a correlated wave function. It just cannot be written as a product. Because of this correlation effect, you have an extra term in the force, and that leads to basically other effects that you will not get in standard DFT. So this is basically not included in the DFT LDA or the DFT PBE. It is not included when you do hybrid functionals. And it is quite important because, I mean, most layer materials like graphite, transition metal chalcogenides, all these things which are, kind of sandwich structure without strong covalent bonding between them, the interlayer separation and energy is kind of dominated by this interaction. It is absolutely critical to biological systems like proteins. So all the kind of secondary structure of proteins is all dominated by this kind of effects. So it's very difficult to do biology if you, from using quantum mechanics, if you don't have this kind of effects. And also if you're doing like organic electronics, like pentasync crystals and things like that, without that it's very difficult to get correct answers. So now there are many recipes to basically improve DFT calculations by including some approximation to van der Waals interactions. So all of these are very good, and essentially, depending on the group you are, you may use one or the other. But the point is that there are different approaches which give, maybe not exactly the same answers, but they're all going towards the direction of trying to incorporate this in a way which is as clean as possible, essentially. So these things go from techniques which are more empirical, where you try to really add this in the forces, and then you try to fit this parameter, to something which is more ab initio, where you try to determine everything from within a DFT calculation. So that's a very active research field now, where there are many groups who are developing methods to move forward. So two last slides. This has to do with the GW methods that I mentioned a few times. So this is more about band gaps and electronic excitations, okay, not about structures, although there is now an interest in using these techniques also for studying total energies. That's kind of under development. So the idea is the following. So you have this kind of Kohn-Sham equation, okay? So there was kinetic energy, nuclear, so energy from the nuclei, R3 potential, the electrostatic one, and then the exchange and correlation. And what you are solving these days is an equation like that, which gives you the eigenvalues and so on, okay? So the approximate bit in the story is this exchange and correlation potential. So the idea is maybe one can replace that with something better. And that's, the purpose of Hubbard corrections, hybrid functionals, all these things. So you're trying to do that better. So one can do this better in two ways. Either you try to derive it from, let's say, density functional approaches, where basically you try to write down new functions, new exchange correlation energies using some exact, some rules, and then you find approximations. Or there is another way around, and that's basically saying, I don't want to go there to this point starting from DFT. I take a completely different approach, and I try to study my problem using the techniques developed for quantum field theory, okay? So things like quantum electrodynamics stuff. So basically what you discover, if you start from quantum field theory and you look at let's say energetics and dynamics of electrons using Green's functions, okay, which are like a mathematical tool to study the propagation of electron in a solid, you end up actually magically with an equation which is not very different actually, and the main difference is that instead of having this object here, you have a slightly more complex function which depends on two electron variables and on an energy, okay? So this object is called self-energy, all right? So this actually is an exact statement for essentially these objects, which are no longer wave functions, but it's something which is called Dyson's orbitals, okay? It's something which exists in the world of quantum field theory. But clearly you see the analogy between those two. So you can also, instead of doing quantum field theory, we can look at that, compare to that, and say, oh, maybe actually everything is more or less the same, but I can try to think of this as a better version of that, okay? So that's an easy way to see it. Now the complication in this story, so I didn't specify how this is calculated, but we do that in a second. The complication you see here is the following. So this is the same eigenvalue you see here. So this depends on the energy, And this has to be solved for an energy which is the same on the left and the right. So we are losing the standard eigenvalue problem, which is so nice here, basically. The second thing is that this object, in the most general case, is not Hermitian, okay, and is complex. So we are really talking about a completely different beast. And that's actually probably the most general way of looking at the wave functions and the eigenvalues. So one approximation which has proved very successful and is becoming extremely widely used is the so-called GW approximation. Okay, so basically this is written as the product of a Green's function, G, and W is the screen and Coulomb interaction. So it's the Coulomb interaction, let's say, divided by the dielectric function of the solid. Okay, so this is what people think of when they mention the GW approximation. So you place this thing here, and then the point is, in principle, we would like to solve everything. In practice, that is difficult. At this point, what people do is something called many-body perturbation theory. So instead of trying to solve this equation, which is difficult, what one can do is to solve that, okay, and then add the difference between this and that as a perturbation, okay, like first-order perturbation theory. So basically, the expectation value of the wave of this on a wave function is the shift of the eigenvalue coming from this theory, okay. So I know this is a bit too advanced, but I just want to give you a very, very, quick, kind of summary of what people are doing. So basically, the main problem of that is that it scales with the fourth power of the number of atoms. Standard DFT scales with the cube of the number of atoms. Okay, so we go one order up, and that's actually quite challenging. Okay, so if in DFT you can do calculations with now, I guess 2,000 atoms is reasonable. It's a bit, it's an effort, but you can do calculating with 2,000 atoms now, without using linear scaling techniques, which are more advanced. In GW, you cannot do the same. You maybe by pushing the same way, you can go to maybe 100 atoms. So it's, it really constrains the sizes of the systems, of the complexity that you can look at, because it's much more sophisticated. So why people like this technique? This is the same plot I gave you before for the band gaps. Blue was DFT LDA, what we've seen before. So now red is band gaps calculated using this GW technique. So you see that most of them fall almost bang on this diagonal line. And this calculation is entirely from first principles. So there's absolutely no adjustable parameter whatsoever. Okay, so that's why this is very powerful. And this is my personal view of the problem. And so this contains most of the physics that we need to incorporate. So probably is a very promising way forward. So there is a lot to do in this area. And I want to give you just one. Okay, go ahead.
How well does the GW method do on transition, the 3D and the 4Fs?
Yeah, that's the question. I was hoping not to get this. So it doesn't. Essentially the point. Let's put it this way. So this, the way it is done, it is in like a perturbation. So this, I say, is difficult. So basically, nobody does that. So what people do is calculate first DFT eigenvalues, and then find the corrections by taking basically expectation value of the difference between these two potentials. So what does it mean? In perturbation theory, if you take the correction, you basically are doing the sandwich of the delta potential with respect to wave functions, and the wave functions are the ones you started from. So that would be DFT LDA wave function. Then, if you're looking at the example I was giving before of iron oxide, if in DFT it's metallic, there is no way that this will transform into an insulator, because the wave functions are already been kind of made into a metal in a sense. You see what I mean? So you cannot transform like a metal into an insulator. So if the screening properties and the qualitative kind of features of the system are completely wrong, incorrect, this will not fix it. If the system is already insulating, you have a small gap, there is very high chances that by using this, you will get a gap which is much closer to experiment.
So when you do the perturbation, you only calculate the energies, you don't recalculate the
That's a good point. So there are essentially there are 2 or 3 levels. Basically, most people would do basically this thing. So look just at the shift of the eigenvalues in first order perturbation theory. That's what is done. And that's because it's the cheapest thing to do. What you can do also is to try to calculate the variation of the wave functions. That goes towards the direction of something called self-consistent GW, which is more advanced. And that is something which is becoming slightly more popular now, but it's, it will take some time to. Essentially, there is a lot of debate now on what exactly needs to be done, and there are many recipes possible. And I think we're still trying to figure out what is the if there is a consensus on how to proceed on that, basically. I think this is the last slide, and I will be very quick. Maybe I will just give you a plot to give you an idea, because it gets very technical. I mentioned this is mostly for people looking at optical properties. I mentioned that in the case of silicon, we were missing a peak, which was coming from excisions, okay? So those things now can be calculated using something called the Bethe-Salpeter approach. This is also a technique which derives from quantum field theory. In this case, since an exciton is about two particles, this is done using basically studying the Green's function of two particles. So basically, it's got two particles Green function, okay? We're going, one level up in terms of complexity, and essentially one can study these things using essentially linear algebra problems, and the whole story is contained to something called an interaction kernel, which is the Coulomb interaction between electrons and holes. So maybe we can skip this thing, which is a bit technical, and I can show you one example. So what you see here is basically lithium fluoride is a typical example. So the yellow is a DFT calculation of the optical absorption, okay, and the gray is a experimental absorption, basically the absorption spectrum, okay. So this is a very common example, which is used as a prototype to show how these things function. So the actual band gap is maybe 14.5 eV, and what you can see is that the experiment gives a very strong peak, which is below the band gap, and which is not captured at all by the calculation. This is not a problem of DFT. It is a problem of the independent particle approximation, where you are not taking into account the interaction between the photoexcited electron and the hole left behind. So if you take this interaction into account, you get this plot where you see that there is an excitonic peak. So this is much better now, and this has been obtained using the Bethe-Salpeter equation, okay? So this is probably the most advanced techniques that you will see around today to study optical properties in the presence of strong electron-hole interactions, okay? So that's basically, but we are talking here about things which are non-standard in the sense that it is not something that, you take a software, you press a button, you get a number. This requires a lot of babysitting, and one has to be very careful in running these calculations, because it's quite specialized, and there are many challenges to overcome. And typically the way it goes is one does a DFT calculation, then runs a GW calculation to get correct band gaps, and then one runs on top of that a Bethe-Salpeter calculation. So it's like a bit we did for the electric constant, the DFT, then the phonons, and the electric constant. So one builds up, and these things are quite fancy. So if you can do a nice calculation with Bethe-Salpeter, you may get a nice paper out, because not many groups can do that. Okay, so I think this is it, and I want to say thank you, because I had a lot of fun this week. So this is, I guess, the end of the story. Right? So in the afternoon, we will try to calculate band structures, and it will be difficult that you finish also calculation of optical spectra, but it's described there. So if you want to because it's a bit long, the tutorial, but I wanted to put it there. You don't need to finish, but if you go home and you want to try, it's there, so you see what it is about. But I think if we can manage to calculate the band structure, I don't know, of I think strontium titanate and graphite, and visualize the wave functions of graphite, that would be nice. Okay, so we adjourn at 1:30.